Let us start by a brief introduction on water. In this picture, we can see an overview of water treatment process. The raw water is delivered to the headwork of the water treatment plant. The 5 major unit water treatment processes start the treatment to make the water clean and clear. The 5 major unit processes include chemical coagulation, flocculation, sedimentation, filtration, and disinfection. Let's note down the different processes involved in unit water treatment process. Screening, coagulation and flocculation, sedimentation, filtration, softening, ion exchange, reverse osmosis, deaeration for corrosion inhibition, and disinfection. Let's start with screening, which is the first process in water treatment. So, its main purpose is to protect the structure downstream against large objects which might create obstructions, easily separate and remove large matter carried along by the raw water, which might negatively affect the efficiency of later treatment procedures or make their implementation more difficult. The usual screen spacing is: for surface water upstream the strainer, it is between 20 and 40 mm. For raw water, from 15 to 30 mm, and for sludge, if necessary, 10 mm or less. For some industrial effluents, especially agri-food effluents, fine bar screening. Here is the layout of bar screens. A bar screen is a mechanical filter used to remove larger objects such as racks and plastics from wastewater. It is part of the primary filtration flow and typically is the first or preliminary level of filtration being installed at the influent to a wastewater treatment plant. They typically consist of a series of vertical steel bars spaced between 1 and 3 inches apart. After the water comes out of the bar screens, it undergoes another process called coagulation and flocculation, which are used to separate the suspended solid portion from the water. The small particles are stabilized by the action-repulsive force that results from the negative surface charge present on the particles. Coagulants with opposite charges of the suspended solids are added to the water to neutralize the negative charges on dispersed non-settlable solids such as clay and color-producing organic substances. Once the charge is neutralized, the small suspended particles are capable of sticking together. The slightly larger particles formed through this process are called microflocs. A high energy is required to properly disperse the coagulant, and particle collisions is needed to achieve good coagulation. Proper contact time in the rapid mix chamber is typically 1 to 3 minutes. Inorganic coagulants such as aluminium and iron salts are most commonly used. When added to the water, they furnish highly charged ions to neutralize the suspended particles. The inorganic hydroxides formed produce short polymer chains which enhance microfloc formation. Common coagulant chemicals used are alum, ferric sulfate, ferric chloride, ferrous sulfate, and sodium aluminate. The first four will lower the alkalinity and pH of the solution, while the sodium aluminate will add alkalinity and raise the pH. Polymers are becoming more widely used, especially as coagulant aids together with the regular inorganic coagulants. And ionic polymers are often used with metal coagulants, and cationic polymers may be used alone or in combination with the aluminium. When we see flocculation over coagulation. Flocculation is a gentle mixing stage that increases the particle size from submicroscopic microfloc to visible suspended particles. These microflocs are brought into contact with each other through the process of slow mixing. Collisions of the microfloc particles cause them to produce larger visible flocks called pin flocks. The flock size continues to build through additional collisions and interaction with inorganic polymers formed, and then microflocs are formed. Once the flock has reached its optimum size and strength, the water is ready for the sedimentation process. We all know that sedimentation is the process of settling or being deposited as sediment. But all that is not enough. To know more, let's meet Mr. Ashok, who will be telling us about sedimentation in more detail.
Sedimentation is a treatment process in which the velocity of the water is lowered below the suspension velocity and the suspended particles settle out of the water due to gravity. The process is also known as settling or clarification. Most water treatment plants include sedimentation in their treatment processes. However, sedimentation may not be necessary in low turbidity water. In that case, coagulation and flocculation are used to produce pinpoint, very small floc which is removed from the water in the filters. The most common form of sedimentation follows coagulation and flocculation. This type of sedimentation requires chemical addition in the coagulation or flocculation step and removes the resulting floc from the water. Sedimentation at this stage in the treatment process should remove 90% of the suspended particles from the water, including bacteria. The purpose of sedimentation here is to decrease the concentration of suspended particles in the water, reducing the load on the filters. Sedimentation can also occur as part of the pre-treatment process, which is known as pre-sedimentation. Without coagulation or flocculation, plain sedimentation can remove only coarse suspended matter, which will settle rapidly out of the water without the addition of chemicals. Pre-sedimentation can also be called plain sedimentation because the process depends merely on gravity and includes no coagulation and flocculation. This type of sedimentation typically takes place in a reservoir, grit basin, debris dam, or sand trap at the beginning of the treatment process. While sedimentation following coagulation or flocculation is meant to remove most of the suspended particles in the water before the water reaches the filters. Pre-sedimentation removes most of the sediment in the water during the pre-treatment stage. In addition, pre-sedimentation basins are useful because raw water entering the plant from a reservoir is usually more uniform in quality than water entering the plant without such a holding basin. Clarifier or settling tank is used to carry out the sedimentation process. Let us see what are types of basins. There are basically three types of basins: rectangular basins, double-deck rectangular basins, square or circular basins. Rectangular basins are the simplest design, allowing water to flow horizontally through a long tank. This type of basin is usually found in large-scale water treatment plants. Rectangular basins have a variety of advantages: predictability, cost-effectiveness, and low maintenance. In addition, rectangular basins are the least likely to short-circuit, especially if the length is at least twice the width. A disadvantage of rectangular basin is the large amount of land area required. Double-deck rectangular basins are essentially two rectangular sedimentation basins stacked one atop the other. This type of basin conserves land area but has higher operation and maintenance cost than one-level rectangular basin. Square or circular sedimentation basins with horizontal flow are often known as clarifiers. This type of basin is likely to have short-circuiting problems.
Thank you, Mr. Ashok, for the valuable information. The water after sedimentation is carried out into the clarifier. Clarifiers are nothing but settling tanks built with mechanical means for continuous removal of solids being deposited by sedimentation. Circular clarifier with surface skimmer visible in the lower right. As the skimmer slowly rotates around the clarifier, skimmed floating material is pushed into the trap visible above the fenced enclosure at the lower left. The most commonly used settling tank is rectangular sedimentation tank, which has effluent weir structure visible above the fluid surface. These rectangular sedimentation tanks are called settling tank. As soon as the water leaves rectangular tanks, it is undergone water filtration, which is the process of removing suspended solids and contaminants from water in a granule media filter. The filter media is contained in a pressure vessel of steel. The filter bed is typically 1 to 1.5 meter deep. The filter vessel usually has about 30% freeboard to allow for expansion of the filter bed during backwashing. We know that filtration removes contaminants, but there is much more behind this, which is filter operation. The filter medium used is sand, but other materials like anthracite, garnet, manganese dioxide, granular activated carbon, dolomite and others are used for special applications. Water enters the top of the vessels and flows downwards through the bed of media and leaves through a collector system at the bottom. Contaminants are removed through straining or adsorption depending on the chosen media. Water is passed through the filter until either the head loss across it rises to preset value. It is then taken out of service and cleaned by backwashing with clean water. The backwash water enters the bottom of the filter vessel and flows upwards through the media bed, which starts to fluidize. That are the media grains begin to separate from each other and to float freely. The fluidization of the media releases the retained contaminants, a process which may be assisted by doubling air through the bed, which causes the sand grains to rub against each other, dislodging the retained contaminants from the surface. The contaminants are then washed from the bed and out of the filter to waste. Did you know? Water expands by 9% when it freezes. The important part of water filtration is the pressure filter, which plays a major role in water treatment. Granular activated carbon is widely used to remove chlorine from main water supplies prior to treatment by ion exchange or reverse osmosis, since it could cause damage to the resins or membranes. Dechlorination by activated carbon filtration also removes the taste associated with chlorine. Activated carbon filtration is also used to remove a wide range of organic chemicals, including chlorinated hydrocarbons, pesticides, and the species that cause taste, odor, and color. Manganese dioxide is used as a catalytic filter bed to remove iron and manganese from borehole water for a range of industrial applications. Similarly, dolomite or limestone chips are occasionally used in filters, either alone or as a separate layer above sand to neutralize low pH waters. The media slowly dissolves and has to be replaced at regular intervals. Because filtration is a batch process, filters are usually built in batteries consisting of 2 or more filters so that filtration to service can continue while one filter is being backwashed. Now that you have completed the module, it's time for you to check your knowledge